Welcome back, students. In the last video, we talked about ferromagnetic materials. We said a ferromagnetic material will have lots and lots of domains, the tiny volumes, where the material does have a net magnetic dipole moment. But then it has so many of these domains whose dipole moments are arranged randomly, so the net dipole moment of the material as a whole would be 0. Even though the tiny volumes, the domains have dipole moments, because they are going to be vectorially added, and since they are randomly oriented inside the material, the net dipole moment of the material, the net magnetism of the material is 0. So this is what we talked about. And different materials will have different domains. For example, like if you have iron, then it will have a certain arrangement of its domains. And if you have nickel, cobalt, all these things will have different domain structure. But pretty much all of them will have this domain. And if you subject them to an external magnetic field, and then these domains will try to align with the applied magnetic field. So, if the applied magnetic field is not that strong, then only a few domains will align. And if the applied magnetic field is very strong, many more domains will align. And if the applied magnetic field is removed, then the domains that are aligned would, for the most part, would try to remain in that position. So now you will have a net magnetism from the ferromagnetic material. So this is what we saw. And if I keep increasing the strength of the external magnetic field, more and more domains will align. And if all the domains are aligned, then you get the saturation. And beyond that, even if you increase the strength of the external magnetic field, this ferromagnetic piece will not get magnetized anymore, because all the domains are now aligned in the direction of the applied magnetic field. So beyond that, no more magnetism is possible for this piece of ferromagnetic material. So this is what we saw in the previous class. And we also talked about hard ferromagnetic materials and soft ferromagnetic materials. And hard ferromagnetic materials are the materials which will retain the magnetic field even after the external magnet has been removed from its presence. And soft iron material or soft ferromagnetic materials are the materials which will lose the magnetism as soon as the external magnetic field is removed. Even if they don't lose fully, they will have very little retention of the magnetism that it gained in the presence of the external magnetic field. So this is what we saw yesterday. And today we are going to use this idea, use this concept to talk about something called as the hysteresis loop. You will get to know about it as I proceed. This is how we are going to do it. I'm going to take a ferromagnetic material. Okay. So that would be this. So this will have its own domains. So initially, the magnetic field of these domains are randomly aligned. Magnetic dipole moment, so the domains will have their own dipole moments, but they are randomly aligned, something like this. Something like this. So this is magnetic material. Now I am going to subject it to an external magnetic field. So how can I do that? Well, I can either bring an external, another magnet near that piece. So in that case, I am subjecting it to this magnetic field. But the best way to do it would be to wind a coil around it and then pass current to the coil. So you know that a coil with a number of turns will act as a magnet. So if I keep this material inside that coil, then this material is subjected to the magnetic field of that coil. So the domains will align. Let's do that now. Let me use this color maybe. Okay, I'm going to use this coil. Okay. So if I pass current through that coil, then there is a magnetic field set up by the coil in this direction. So these little magnets, the domain magnets, will try to align. Not all of them will align, like the magnetic field is weak. Only a few of them will align. Okay. Then let's see what happens now. Let me pass current I through this. Okay. If I pass current I through this, then the field set up by the coil is actually B naught, which is equal to mu naught to N to I, where N is the number of turns per unit length and I is the current flowing through this coil. And because of the presence of this B naught, then these domains will try to align. Okay, and the net magnetic field of this bar magnet would be something like this. I am giving an approximate idea, but this general discussion is enough actually. Okay, to understand the concept. So B of this field, okay, that is going to be equal to mu naught and then mu r into N to I. Let me put it this way. So mu r is the permeability of that material, and N and I is as usual the number of turns per unit length, and I is the current which is flowing through. So this is a net magnetic field there. So the extra magnetic field is given by this material, and this is a very small number, but then like mu r is very high. It could be more than 1000. So in that case, this field, because of this material, would be much stronger than otherwise. Anyway, so let's see like what are the things that you can control here as far as this is concerned. I can't control mu naught, that's a fixed number. I can't control mu r, that is actually, that depends on the material. The relative permeability depends on the material. For iron you will have one value, and for cobalt you will have another value, for nickel you have yet another value. So you can't control this. But what can you control? You can control this N and I. I can have more turns per unit length, that is in my control, and I can change the value of the current that is flowing through the coil. So those are in my control. So we already discussed that that this is called, this Ni, which is in my control, is called as the magnetic field intensity. So this is in my control. So this I can vary, and if I vary this, then this will vary. Now I can plot a curve. I hope you are able to see that. Like, I can plot a curve where this is in my x-axis and this will be in my y-axis, because this is the independent variable which is in my direct control. I can vary that independently, but if I vary this is going to vary. B is going to vary. So that's the dependent variable. So you know that you will have independent variable along the x-axis and a dependent variable along the y-axis, and that is how you plot a curve. Okay. So let's see what happens if I do that. So I'm going to have this. So this is my results one. Okay. So along the x-axis, I'm going to have h, and along the y-axis, I'm going to have b. Okay. So this is like this. I'm going to do it for one material. Let's say like I've taken an iron piece, or a cobalt piece, or a nickel piece. I've chosen the material. Once I've chosen the material, I have no control over this. I have control over only other stuff. So this is let's see what happens now. The general idea. Okay, let's see. How do I increase? How to vary h? I'll vary h by varying the current, because once I've chosen the wire, I can't do much about n, so I'll vary I. So I'm going to vary I now. So if I vary I, then I'm setting up this magnetic field B0, and because of that, some of the domains will get aligned with the applied magnetic field. Okay, let's see. So I'm going to have first, this is my current, h is 0. Okay, my current is 0. If current is 0, h is 0. So here I'm going to start. Right now there is no net magnetism for this piece. Okay. What I'll do, I'll increase the current. If I increase the current, then a little bit. I'm going to give it some amount of current, which means that some of the domains will align. Maybe this aligns with this, maybe this aligns, and maybe this also aligns. So now the rest are not aligned so much, but now you see, before this it was 0, now you will have a small magnetism for this one. So I stop the current, and if I stop the current, and if I measure, this is going to reach time, right? So I stop the current, and if I measure the magnetic field strength, then I get some value for it. So for this particular thing, I may have something here. I'll have some value. And now I increase the current from here, from this value to some other value. So my H increases. As my H increases, then the magnetization also increases. Okay? So I keep doing it. So when I increase it, a few more will be maybe these two align with that field. And this keeps increasing. As I keep increasing the current, you see, this keeps increasing. But you see, there is a limit to it, because there are only a limit, a finite number of domains in this material. So I keep increasing current, and more and more domains are getting aligned with the magnetic field, because the applied magnetic field strength is increasing. Because applied magnetic field strength is increasing, the domains in this piece are also more and more domains in the piece of material, ferromagnetic material, are also aligning with the field. So, as the more and more domains are aligned, B value also increases because we're producing greater and greater magnetic field. Okay. But then there is a limit, as I said. Okay, there are only a finite number of domains. So as I keep saying, it is going to reach saturation. Okay, so it's going to reach saturation like this. Okay, and it will remain because maybe at this point, it is at this h value. Let us suppose that all the domains are aligned in the direction of the field. So beyond that, even if you increase, the B value is not going to change. So it's going to remain like this only. It's not going to change. It's almost saturated the whole thing. Every domain is aligned. So increasing the current value would not make any difference at all. Because all of them are now aligned in the direction. All of the domains are now aligned in the direction of the applied field. Okay. Now, if from here I'm going to reduce, I've reached a certain value of I, where I've reached the saturation. Beyond this, I can't have any more magnetism. Now I'm going to reduce the field. I'm going to reduce the current. If I reduce the current, then what happens is that it won't, suppose I reduce the current to this. Okay. From here, I reduce the current to this value. It won't come back to this. The magnetic field will not come back to, magnetic field strength now will not come back to this. Once I have magnetized it, then if I reduce the current, I won't get back, I won't retrace this path. Why? Because previously they were all randomly aligned. Now they are all aligned in a particular direction. See, now the situation is different. So if you reduce the current, only it's almost like the aligned fields will try to stay there, because now they have a new orientation. Now they are not random; they have a new orientation. So even if we remove the magnetic, remove the current, they'll try to be there. They'll try to stay in that position. Some of them, because of the way that you remove, the current kind of because of other effects. Some of the domains may get disoriented, but most of them will remain in their position. So even if I reduce the current, and once I reach this place, then it will almost remain the same. So even if I bring the current to zero value, it will almost remain the same. Think about it. So from here, maybe a slight variation, but then this will remain the same. As I keep reducing the current, I won't retrace that path. I'll be here because they're already aligned. They're no longer random. I hope you understand this. So what happens here is that this will come back like this, almost the same, will remain almost the same. So this is the saturation point A, and if I bring the current back to zero, the magnetism of this material will not become zero, it will not become totally random, but then it will have some value, maybe a slightly reduced value, but it will have some magnetism there. Okay? So this is what I call as BR. That is, the magnetic field, field strength retained by this piece of material, even though the external magnetic field has been removed. You are using the external magnetic field to magnetize this material. So now more and more domains are aligning. Now you reach saturation. Now you remove the magnetic field. In this case, you are switching off the current. The current is now 0. Suddenly all these field domains are not going to become random again. No, they are already aligned a certain way. There is some equilibrium reached. So even if there is some slight disturbances, it is not going to lose all of it. So it will still retain a lot of magnetism. Again, that depends on the material. You know, like some materials will try to have high retentivity, so they will maintain, they will retain a lot of magnetism after aligning. Some materials are not that retentive, so they may lose a lot of it, but may still retain some amount of the magnetism that it reached. But the point here is that even if you reduce the current to 0, now this material will not go back to its original state of not having any magnetism at all. Once you magnetize something and then remove the external magnetic field, the magnetized material will still retain some amount of magnetism. So that's what you are seeing here. So this would be position B. So if you come back to, so you magnetized it, it went like that, and as you keep reducing the current, then it came like this. Okay. But how do you bring it to 0? How do you demagnetize it? Well, now most of them are aligned here in this direction now, right now. Okay, most of them are aligned in this direction. Now what you need to do is that you need to pass the current in the opposite direction. We are passing the opposite direction. Now you are going to set the current, the field, in the opposite direction. Now some of them will try to orient in the opposite direction. So reverse the current direction. If you reverse the current direction, then some of them will reorient in this way. So the net field may be like, as you go from here to some value I, this value, by reversing the current, and maybe these two domains will be flipped in the opposite direction. So then what happens is that the net magnetism of this material comes down. So I keep doing it now. So I keep increasing the current in the opposite direction, and now I reverse the current direction. So this time I'm going to reverse the current direction. Okay. Reverse the current direction. So current is going like this. So as I keep doing it, then more and more fields will flip. So you see, then it will be coming like this. Okay. So but some value of the current in the opposite direction, the number of domains which are in one direction and the number of domains in the other direction would be equal. In that case, there would be no net magnetism C. Okay. This value is called along this. Well, B is 0 anyway. Now B is 0. Notice that you brought B to 0. But now to bring it to 0, now what you got here is that you need to give current in the opposite direction. So that value is called HC. Okay. This is the magnetic field intensity, which brings this magnetism back to 0. So you are forcing it, once you magnetize something, to bring it back to 0, you need to force it to bring it to 0. So you have to coerce it to bring it to 0. So coercion means that. Coercing means forcing somebody to do something. So coercion. So you are coercing this to come back to 0. So this is called as the coercivity. This is retentivity BR, and here you notice that this is coercivity. You are coercing this. Okay. So now let HC is amount the field intensity to bring it back to bring the magnetism back to 0. Now you continue. Okay? You have coerced it to become 0. So now if you keep giving the current in this direction now, so now you see more and more fields will align in the opposite direction. So now the magnetic field will flip. Previously this was north and this was south. And now since you are magnetizing in the opposite direction, now from zero this will become north and this will become south, but a weaker field. So as you keep increasing, then that field, the opposite field, will become stronger and stronger and stronger. Then more and more domains will keep aligning in the opposite direction, because you reverse the current direction. This will go all the way. And as usual, this will here also, as you keep increasing, more and more domains will align, and finally all the domains will align in the opposite direction. So then you will reach some kind of a saturation in this case. Okay? And once the saturation is reached, once all the domains have flipped in this direction, any more magnetism is possible. Once that no more magnetism is possible, you cannot magnetize it anymore, because you have magnetized all the domains in the direction. Again, so that is saturation. And if we reduce the current, we keep reducing the current, then it will try to retain it. You notice here. So even if it reduces, it will reduce only by a slight amount. Okay, so this, even if we bring the current back to 0, so this will still retain some magnetism here in the opposite direction. And if you want to bring it back, and notice to 0, then I have to do it. So now I need to reverse the currents now. The direction has to be reversed. So now let's come back. Maybe to become 0. Then if I keep increasing, then you see it's going to be something like this. Okay? So notice that you have a curve like this. I hope you understand this. You take a material which, a ferromagnetic material, which does not have any net magnetism, then you start magnetizing it. The way you magnetize it is by doing this. Okay, like you have coil, and then you like pass current in that coil, then more and more domains will align. So then like the magnetism of that coil, of the material increases, and finally for some magnetic field intensity H, then all of the domains will be magnetized, they'll be aligned in one particular direction, and you have reached saturation. And increasing the current beyond that will not do you any good, because there is nothing more to align. Everything is already taken care of. So then you reach its saturation point, and then you come back to this. Then like if you keep reducing the current, and then when you do that, when you make the current 0, it is not going to lose all the magnetism that it has gained. It will still retain some magnetism. So if you want to bring it back to 0, now you need to send the current in the opposite direction, so that at least some of the fields will will align in the opposite direction. So as you keep sending current in the opposite direction, more and more domains are aligning in the opposite direction. So the net field is getting reduced, and finally for this value of Hc, you have coerced, you have forced the magnet, the material to lose all of its magnetism. Okay, so it reached here 0, and now you continue in that opposite direction, send more and more current, then you see more and more domains will start flipping in the opposite direction, and finally you will reach saturation in the direction. So what was once north has now become south, and what was once south has become north. So you do that here. And again, if you bring the current back to zero, it is not going to lose all the magnetism. Like the saturation magnetism it had attained. It may lose a bit of it, but then it will retain that. Some of the magnetism there. Now you continue in the other direction, the original direction, to bring it back to zero. So notice that for a particular value of H, you are not going to have a single value of B. If you look at this curve, if this was unmagnetized, then this is the value of B for the particular H. But if it had already been magnetized, notice for this H, then you may get this value. So it depends on the history of the material. So what value of B you are going to get for a particular intensity depends on whether or not the material has been magnetized before, and in which direction. Clearly, for this you may have this also, depending on that. So you see, for one particular H, you end up with multiple values of B. So this phenomenon is called as a hysteresis loop. Hysteresis loop or curve of a material. So different materials will have different curves, but the shape is this. The shape of the hysteresis curve for all the materials will be the same. Hysteresis loop curve, you call this. So hysteresis does not mean history; it means lagging behind. Actually, it means lagging behind. Clearly, you lag behind, because you don't become zero when I is zero, because the magnetic field lags behind the current. So then, as the current proceeds more in this direction, then it comes finally it becomes zero. When the current is more negative, then it is zero. So that is what you say as hysteresis. It lags behind. The field lags behind the magnetic field intensity. B lags behind H. Field lags behind the magnetizing current. Okay. So this is what you call as hysteresis. So different materials will have different hysteresis curves, but the shape of this curve is same for them all. You may have one value for iron here and another value for nickel and cobalt, but then all of them will have essentially this shape. Only the values will be different, but the shape of the curve is the same. Okay. So there are two terms that you should know when we talk about the hysteresis loop or curve. One is retentivity and the other one is coercivity. What is retentivity? Retentivity is a value of the magnetic field strength B when you have stopped magnetizing it, like you have stopped the current. When I is 0, when H is 0, then what is the value of the magnetic field strength? And this is retentivity. So you take a ferromagnetic piece and then you magnetize it, and then you stop magnetizing, then it is going to retain some of the magnetism. And that value of that magnetism, B or magnetic field strength, is retentivity. And what is coercivity? Coercivity is the amount of H you need to have to bring it back to zero. Bring the magnetic field strength back to zero. You need to coerce that piece to become a non-magnet again. So this value the value of H at this place, if this is A, B, and I'll call this as C, and the value of H at C is coercivity. HC is the value of H that makes magnetic field to become 0. So it is like this. Retentivity is the value of B when H is 0, and coercivity is the value of H when B is 0, once it is magnetized. Okay, so these two are two terms that you need to know. Second, as I said, different materials will have different hysteresis loop. The general shape will be the same, but then these values B and H, those values will be different. It is like this. Suppose some materials will have a curve like this. Okay, will have a strong retention and then can become something like this. So a very thin curve here and then very tall curve. What it means is that the retentivity is high. Even if I stop my H, then this becomes, it retains a lot of the magnetism that it obtained. But then if this H is small, then it can lose it quickly. It can become 0, magnetic field becomes 0 even with a little amount of current in the opposite direction. So it has low coercivity and high retentivity. Retentivity is more because once you stop the current, it still retains a lot of magnetic field. But then I can bring the magnetic field back to 0 with a little bit of coercion. With a little bit of force, I can bring it back to 0. So low retentivity and high retentivity and low coercivity. And some other material may have a curve like this. I'll draw it here. Okay, so it may have a low retentivity. It's maximum saturation, but as you bring it back to 0, then the field strength may come considerably lower. Okay, but then you can also something like this. Okay, we put it this way. Something like this. You see, the saturation is high, but then when you stop the current, then the alignment, it's not that great and comes back to, it loses a lot of magnetism here. So it reduces a lot, so it has low retentivity. So this is BS, the saturation magnetic field strength, and this is your BR. So BR would be much less than BS. So now it has low retentivity, but you notice here, this is, I need to bring, I need to force it too much. I need to send a lot of current in the opposite direction to make the field 0. So I'll say that this has low retentivity but high coercivity. And it is like there could be some materials which may have high retentivity and also high coercivity. So those are the materials you would use for permanent magnets. So you magnetize something, then you stop the current. Okay, you take a material, you magnetize it, you reach by sending current, then it reaches the saturation value, and then you stop the current, and it should retain most of the magnetism that it obtained while it was getting magnetized. So it should have high retentivity, and also once you get a magnet, then it shouldn't lose it very quickly. It should not be affected by stray magnetic fields. Some other magnetic field should not make it lose this magnetism. So you drop it, and then the molecules are, like they are subjected to certain force. Then they align in a randomly. They shouldn't get aligned. In that case, also you will lose magnetism. So if you are looking at making a permanent magnet, and that material must have high retentivity and high coercivity. High coercivity means that it won't lose its magnetism quickly. High retentivity means that it will retain the magnetism even after you bring the current back to zero. Okay? And these materials must have high permeability, right? Because only when you have high permeability, magnetic field strength will be high. So you should have high permeability and high retentivity and also high coercivity for permanent magnets. And for electromagnets, well, you should have high permeability, certainly, because you want to have a great field strength. So high permeability must be there. Okay? And what should happen? The moment you stop the current, it should lose its magnetism. Otherwise, if it still maintains magnetism, then you can't have a good electromagnet. What are electromagnets used for? Let's say one of the applications would be picking up a wrecked car. Okay, a car is wrecked, so now you want to move it from one place to another. So you bring a big electromagnet. That magnet comes down. Okay, using a crane, you bring that piece. Okay. Now you magnetize it. You send a current. Now it becomes a big magnet, very strong magnet. Then it picks up the car. Then it takes it to a different place. Okay. Now, if you switch off the current, the magnetism you should lose immediately. Only then the car will fall. So, if the retentivity is high there, if you switch off the current, it will still get stuck to the piece, a ferromagnetic material. The car won't fall, but that is not what you want. So, for electromagnets, you want high permeability, all right, but then you want low retentivity. It should be very, very, very small. Okay, so these are the things. So for permanent magnets, you need high retentivity, high coercivity, and high permeability. For electromagnets, you need high permeability, all right, but then retentivity must be small. So once you switch off the current, then it should go back to almost zero. So these are the materials you would choose. Soft iron is one such material which has high permeability, all right, but low retentivity. And that is why you are using soft iron in transformers and in electrical instruments. Even like the moving coil galvanometer, you talked about the soft iron core. So it's because like the moment you stop the current, then it should lose its magnetism. If it doesn't lose the magnetism, it will still have the magnetism. It will get aligned with this the permanent magnet in the moving coil galvanometer. So you don't want that to happen. So for all these equipments, we use the soft iron core because it has low retentivity, very low retentivity. So for permanent magnets, you need high retentivity and high coercivity. The permanent magnet should not lose their magnetism very quickly. And for both, you require high permeability because you want to maximize the field strength when you want it. Hope this is clear to you.